It's a topic from module 5, which is approximation algorithms. So in the approximation algorithms, you will see two types of problems. One is bin packing and the other one is graph coloring. So what are approximation algorithms? We know that this NP hard problems, which will take the more complexity, time complexity, those problems cannot be solved in polynomial time. It takes exponential time. NP hard problems or NP complete problems, they will take exponential time. So finding an exact solution for such type of problems is time consuming. But what if the finding an approximate solution we can find in less time, means we can go for the approximate solution instead of finding the exact solution which takes exponential time. We can find an approximate solution for that problem which takes polynomial time. So that approximate solution is a feasible solution, but it is not an optimal one. It is near to an optimal solution. So an approximate algorithm, or another name is heuristic algorithm, for a problem P is an algorithm that generates approximate solutions for P. It will not generate exact solutions, it will only generate approximate solution, but the advantage is in lesser time it can generate the solution. So these are the different features of the approximate algorithm. Approximate algorithm guarantees to run in polynomial time. Approximate algorithm guarantees to seek high accuracy. Approximate algorithms are used to get an answer near the optimal solutions. Now, in approximate algorithm, another term is the performance ratios. For example, we are getting, for an optimization problem, each solution is associated with a cost. For example, to find the shortest path from a source node to a particular vertex node, that is minimum distance. So minimum distance, it will be having a value. So it will have an exact value or an optimum value. Then it can have an approximate value. Approximate value differs from the optimal value, and we can find the ratio of the approximate value and the exact value or optimal value. So optimal value, here it is represented by C star. Optimal cost is represented by C star. This is the exact answer. And the approximate value, it is represented by C, or approximate cost is represented by C. For example, if you are finding the minimum size vertex cover VC, so the approximate value, it can be near to the optimal value. So that ratio is, which is the maximum of C by C star or C star by C, is less than or equal to P of n. The approximation, this is known as the approximation ratio, which measures how bad the approximate solution is distinguished with the optimal solution. If this P of n, it does not depend on n, means it can be written as one approximation algorithms. Some problems have polynomial time approximation algorithms. With small constant approximation ratios. So these are about the approximation algorithm, and we can see one problem which can be used in which can be solved using approximation algorithm. So that one is the bin packing problem. Bin packing problem. Given n items of different weights and bins of each of capacity C. We have given n items and we have given bins also. Each bin is of capacity C. What we have to do here is we have to assign each item to a bin such that number of total used bins is minimized. So we have to pack these items into the given bins so that the number of bins is minimum. It may be assumed that all items have weight smaller than the bin capacity. So here it is 6 items are given here of weights 4, 8, 1, 4, 2 and 1. And bins, we can use bins of capacity 10. So we can use, either you can use one bin. Anyway, these items are not Cannot put into a single bin. Two bins, two bins we can, whether we can accommodate all items, or three bins. So minimum number of bins in which these items can be accommodated. So here it is, the minimum number of bins is 2. The first bin 4, 4 and 2 can be placed. 4 plus 4, 8 plus 2, 10. And in the second bin 8, 1, 1 can be placed. So this way the minimum number of bins here is 2. Now we can see another example in which this is weight. These are the different items, 6 items. 9, 8, 2, 2, 5 and 4. Bin capacity is 10. So here we need minimum 4 bins to accommodate all items. So how to find the minimum number of bins? So to find the minimum number of bins, we have to check with all the permutations or all the combinations of the different items. So it is an NP-hard problem. Finding the exact number, minimum number of bins taken is will take exponential time. So it is an NP-hard problem. We can, the lower bound on minimum number of bins we can find like it's the scale of total weight divided by bin capacity. Total weight of the items divided by capacity of the bin. So this will give the lower bound. It has this bin packing problem have different applications. Loading of containers like trucks, placing of data on multiple disks, job scheduling, packing advertisements in fixed length radio and TV station breaks. So there are different applications for this bin packing problem. But it is an NP-hard problem. So solving or getting an optimal value, the minimum number of bins, the optimal solution is will take exponential time. So we can go for some approximate solutions using mainly 4 approximate algorithms. Here 4 types of algorithms are used. These will not in general give optimal packings, but which will be near to the optimal packing. So they are first fit. These are the algorithms. First fit, then 4 types of algorithms are there. Approximate, those are which will give approximate algorithms. First fit, then second one is best fit. Next is first fit decreasing. First fit decreasing. Then next is best fit decreasing. Best fit decreasing. In this first fit and best fit can be considered as online algorithms. That means this they are processed. The bins, the whenever these items are coming, the bins are filled. Then first fit decreasing and best fit decreasing, already the items are known and it is filled on offline. So those are known as, can be known as offline algorithms. So first we can see what is a first fit approximation algorithm. In this, when processing the next item, scan the previous bins in order and place the item in the first bin that fits. Start a new bin only if it does not fit in any of the existing bins. So each of the items, while it is getting filled, when next item arrives, then we have to check or scan the previous bins. If there is any space, it will be put into that bin. If there is no space, then it will be put into the new bin. So this will take, first fit algorithm takes big of n square times, the polynomial time algorithm, and it can be implemented in big of n log n time if we use self-balancing binary search trees. Now we can consider an example. So here these are the different bins, each of capacity 1. Assuming that the size of the items, these are the items. So items, this 0.5, the size is given 0.7, 0.5, 0.2, 0.4, 0.2, 0.5, 0.1, 0.6. These items has to be filled into these bins. So we can find the lower bound for this one, that is total weight divided by bin capacity. Lower bound is 4 bins. Now how this first fit algorithm works, we can see. So first, the first weight, it is the 0.5. First item is of weight 0.5. So it is filled into the first bin, 0.5. Then second item is zero point 0.7. So it cannot be filled into the first bin because remaining space is 0.5 here. So it is put into the new bin, which is the second bin. Then next item is zero point 0.5. 0.5 we can put this. So this item comes in the first fit. According to the first fit algorithm, we have to scan from the previous bins if there is any space. So here we can find space. So this can be put into this. Third item can be put into the first bin. So the arrangement becomes like this. 0.5 is here, 0.5. So first bin is full. Then next item is 0.2. 0.2 can be placed here. So the next arrangement is like this. Then next item is zero point 0.4. So zero point 0.4 we cannot put it in the first two bins. So we have to take a new bin and put 0.4 here. 0.4 in the new bin. The next item weight is 0.2. 0.2 can be put into the same bin. So 0.2 placed here. Then next is 0.5. 0.5 again here this space is not enough for 0.5. Here it is 0.4 only remaining. Okay, this way. So this is not enough. So a new bin has to be taken. So 0.5 is here. Then 0.1. 0.1 can be scan from the scan in order, which means previous bins are empty means it can be put into previous bins has space means it can be put into that. So 0.1 we put into the third previous bins. Previous bins means it is like we will be scanning from the beginning. So here one space is there to put the 0.1. So the 0.1 will be put in here. Then next is 0.6. 0.6 we have to check the space for 0.6. 0.6 the third first bin it cannot be put, second bin also it cannot be put, third also it cannot be put, then fourth also it is not possible, then fifth bin we have to take. So total 5 bins are required for this first fit algorithm. Then now we can see the best fit algorithm. Best fit means, so according to first fit it is using 5 bins. So it is not an optimal value 5. If less number of bins means that is the optimal value, or even lesser than 5 is possible. So best fit. Best fit is the next approach. In this first fit means in the first we will be scanning the previous bins and if there is space we will put into that bin. Okay. In best fit the idea is to place the next item in the tightest spot. That means the remaining space should be less. After putting that item, the remaining space should be less. That is, put it in the bin so that the smallest empty space is left. Empty space of that bin should be less. Best fit can also be implemented in log and time using self-balancing binary search tree. So same example we can see using the best fit algorithm. Best fit algorithm again we will start with using the first bin. So 0.5 and 0.7 is not fitting into this bin, so it will be put into this next bin 0.7. Then 0.5 it is possible to put in this bin, so it is placed in that bin. Then 0.2 will be placed into this bin. Then 0.4 new bin has to be started for 0.4. Then 0.2 is possible to put here. Then 0.1. So the remaining empty space should be minimum. In such a way, each of the items are put into the bin. Then 0.1 we'll put here. Then 0.6. For 0.6 actually we have to, here one more bin has to be drawn here for 0.6. So this algorithm also, this is for 0.6. This algorithm also takes same number of bins. That is best fit also takes same number of bins as the first fit algorithm. Now the other two are the offline algorithms, first fit decreasing and best fit decreasing. In this what we have to do is we have to sort the array of items in decreasing size, decreasing order. We have to first sort the items then only put into the bin. So here we can see that the same thing, while putting to the bin we will use the first fit decreasing method. So first we have to sort. So after sorting we will get this. Then after that we will put those items into the bin. So first this 0.7 is placed. Then 0.6 means it needs to be placed in the next bin. Then 0.5 another bin needs to be used. Then again 0.5 means this can be first fitting place is this one only. So it is given to this point. This point second 0.5 is given here. Then 0.4. 0.4 above it is 0.6 here, 0.4 space for 0.4 is there, so 0.4 is placed here. Then 0.2 can be placed in the first bin. Then 0.2 again can be placed in the fourth bin. Then 0.1 can be placed in the first bin. So this uses four number of bins is reduced here. So compared to the first fit and best fit, this algorithm works better. Similarly, the best fit decreasing algorithm, in which this works like read the inputs of items, then first sort the array in decreasing order by their sizes, then apply the best fit algorithm. After sorting, it applies the best fit algorithm. So in first fit decreasing, after sorting, it will apply the first fit algorithm. In best fit decreasing, after sorting, it will apply the best fit algorithm. So here it is getting sorted, and then we can see this same procedure. Only in best fit, the condition is the after putting that item, after putting an item, this remaining empty space should be minimum. In such a way, it has to be placed. Then here also this uses 4 bins. 4 bins are required for the solution. Now we can see another example. Another example for this bin packing problem. Bin packing example. So in this example, we have to find the number of bins. Find the number of bins required. Find the number of bins required to put the items. Find the number of bins. Here the number of items n. Now n is the number of items, which is 6, and the weights are 5, 6, 3, 7, 5, 4. So total 6 items are there. And these are the weights, and the capacity, maximum capacity of the bin or bin size equal to 10. So first we can see this how this works with the approximation algorithms. So first we will use the first fit algorithm. So first fit algorithm, how this works we can see. So suppose these are the bins. So this is the first bin. So in the first bin, so this is the each of the capacity of the bins is 10. Up to 10 weight we can place in the bin. So in the first bin, the first item is 5. So I have placed the first item. So till here, this first item is 5. Then second item is 6. So 6 remaining capacity of the bin is 5 only. So we cannot place the item 6 of weight 6 here. So we have to use another bin. We have to take another bin to place the second item. So second item I have placed here, which is of size 6. So here we have a space of 4, and here we have a space of 5. And next item is 3. So 3, where can I place it? I can place in the first fit, means first fitting place it has to be placed. So from the beginning we will see. So here first for the first bin, 4 empty spaces there. Then I can place the bin with weights. I can place the item with 3 here. Then next item is 7. 7 I cannot place in the first bin. I cannot place in the second bin. So I have to use a third bin for placing the item with weight 7. So here is that one. So this item with weight 7 I have placed. Then next item is 5. 5 I cannot place in first bin, second bin, and third bin also I cannot place. So I will be using the fourth bin. I have to take the fourth bin to place the item 5. So place the item 5. Then next is item with weight 4. With weight 4, first fitting place I will search. So it cannot be placed in the first bin, but it can be placed in the second bin. 6 plus 1. So placed. So total number of bins used. Number of bins used. That is the solution. Number of bins used here is 4. But we cannot tell that it is an optimal arrangement, whether less than this is possible or not. Okay. So that's the problem has done using first fit. Now we can see the same problem how we will do it using best fit. The second approach, that is the best fit. So in best fit approach, we have 6 items. The same weights we can use 5, 6, 3, 7, 5 and 4. So best fit means we have to place an item in such a way that after placing that item, the remaining empty space should be minimum. That way we have to place the item. So first item is 5. So it will be, so suppose this is the first bin. So first item I will be placing in the first bin. The first item is of weight 5. Bin capacity is 10. So I will place it here. First item I have placed. Next item is 6. 6 I cannot place in the first bin, so I have to take a new bin for placing the item with weight 6. So I have taken the new bin and I have placed the item here, weight 6. Then next is 3. 3, if I see 3 weight with weight 3, either I can place it in 5 and also I can, then 5 plus 3, 8. This bin capacity becomes 8. First bin, if I place 3, then the bin remaining capacity is 5 plus 3, 8. Then remaining capacity is 2 here. And if I place the second bin, the remaining 6 plus 3, 9. The remaining capacity is 1. So remaining capacity, wherever it is less, that place I had to place the item when we use the best fit. So I will be placing it here. Because here the remaining capacity is 1. If I place in the first bin, the remaining capacity will become 2. So 1 is less than 2. So more tight packing we have to use in best fit. So I place the item in the second bin. The next item is 7, which I cannot place in the first bin and also in the second bin. I will take a new bin for placing that item. So this item is placed till here. This is 7. The next item is 5. 5 I can place in the first bin, because first bin space is there. I have placed in the first bin. Then 4. 4 I cannot place in any of the 3 bins, so I have to take a new bin for this. So in the new bin I will be placing 4. So here after using best fit, we have got the number of bins required is 4. So here also number of bins required is 4. Then next we have to see, we cannot see any advantage of best fit over first fit. So now next we can see the first fit. The third one is first fit decreasing. First fit decreasing. So first fit decreasing means the weights I need to first arrange in decreasing order and then decreasing order of the weights and then apply the first fit. So if I write in decreasing order of the weights, it is 7, 6, 5. 5 comes 2 times. So 5, 5. Then 4 and 3. So this is the decreasing order and I have to apply the first fit algorithm. So here first bin I'll be placing the 7. So 7, suppose it is up to here, 7. Then next item is of weight 6. 6 I cannot place in the first bin. So I will be taking the second bin and placing the item with weight 6 here in the second bin. Then next it is 5. 5 I cannot place in both the previous bins. So I will be taking a new bin and place it here. 5. Then next is again 5. 5 I cannot place in the first fit, means first fitting place I have to see. So I will check for the first bin. It's not possible. Second bin also not possible. Third bin I can place this 5. So I have placed it in the third bin. Next 4. 4 I'll be checking the first bin, it is not possible. Second bin, it is possible. So I'll place the 4 on the second. Then the last item with weight 3, it can be placed in the first bin. So here we can see we have minimized the number of bins. So this gives some more good solution. Minimum number of bins, it becomes 3. So it is a, compared to the first fit and best fit, is a good option. First fit decreasing. Similarly, the best fit, we can see the best fit decreasing method. So but in best fit decreasing, what it does is, again we have to sort the weights in decreasing order. After that, apply the best fit. So the decreasing order is again 7, 6, 5, 5, 4, 3. Then we'll be placing the bins into, sorry, placing the items into the bins according to the best fit strategy. So first it is 7. So 7 is placed in the first bin. Then next item is 6. For placing 6, we need to take another bin. So I have placed the item 6 here. Then next item is 5. 5 cannot be placed in the previous 2 bins. So it will be placed in a new bin. So this is for 5. Then next is again 5. So it cannot be placed in first bins and also second bin, but it can be placed in the third bin. Then 4. 4 cannot be placed in the first bin, but it can be placed in the second bin. So it can be placed here. Then 3. 3 can be placed in the first bin. So here also we will require only 3 bins. 3 bins. So in first fit and also in first fit decreasing and also in second fit decreasing, we will get 3 bins. Minimum number of bins is